Hello, in this lecture we will study power factor and maximum power transfer for AC circuits. Previously, we learned that the average power absorbed by an element in a circuit with a sinusoidal voltage or current source is equal to P is equal to Vm times Im divided by 2 times cosine theta V minus theta I. And here we define another important concept, the magnitude of the complex power S, which is the apparent power, which is given by Vm times Im divided by 2. Now we are defining a new concept called the power factor, in which power factor is the ratio of P to apparent power magnitude of S. And accordingly, Pf is equal to cosine theta V minus theta I. And this angle theta V minus theta I is called the power factor angle. An even function is a function where f of x is equal to f minus x. In other words, an even function is mirrored around the vertical y-axis. Cosine is one such function. Cosine x is equal to cosine minus x. And this causes one problem with the power factor, because cosine theta v minus theta I is equal to cosine theta I minus theta v, and therefore we cannot uniquely determine the phase difference between the voltage and current. Therefore, instead of that plus minus sign, we are using electrical engineering terminology and introduce the words leading and lagging. If theta v minus theta I is greater than 0, we tell that power factor is lagging. In the other case, when theta v minus theta I is less than 0, we tell that power factor is leading. Now let us study a super simple power grid model. Of course, in reality, the power grid consists of many sources and many transmission lines and very many customer loads, but right now let's assume that it consists of from a power plant which creates power, a transmission line which connects the power plant to the customer, and a customer as a load consisting of a resistive and inductive loads. The customer requires power at a specific voltage for instance, running the TV, washing machine, or electrical heater. The transmission line has its own impedance. It has resistance and also impedance. Maybe one day when we have room temperature superconductivity, this will not be the case, but today these are all aluminum or copper wires and they have their internal resistance and inductance. And in general, the power absorbed by the transmission line is lost for the company, because instead of the customer consuming that power, electricity, it is being dissipated as heat over those power lines. So how can we reduce the power absorbed by the power line? So supposedly, in some cases, we might maybe shorten the transmission line by making it pass through an underground tunnel or so. But in general, the length of the wire and specifications of that wire is fixed, and therefore we cannot change R1 or L1. And in general, the customer expects the average power at a specific voltage level, such that they can run some type of appliance which is designed for that specific ratings. So therefore, we cannot change the amount of power which will be consumed by the customer and the voltage. So what can be done? So if we cannot change the resistances, if we cannot remove the resistance or inductance of the power line, maybe a counterintuitive idea might be is to add an additional load to the system and see whether this will help us. The impedance of the transmission line is the addition of these four elements and resultingly it is R1 plus J omega L1. And the power absorbed by the line can be found by finding the real part of this impedance, and accordingly it is Im squared divided by 2 times R1. And since the average power and the voltage of the load is fixed, we can just write this as, assuming that the same current is passing through these elements, average power P delivered to the load is equal to Vm times Im divided by 2 times the power factor. From here, I can calculate Im as 2P divided by Vm times power factor. And if I insert this into this equation, I end up with the power line, basically the average power absorbed by the line is equal to 2 times P divided by Vm times Pf squared times R1. Now I need to figure out how to minimize this. When we look at this equation, we see the Pf in the denominator part. Therefore, increasing the power factor will reduce the power absorbed by the transmission line. Power factor is given as cosine theta v minus theta I. So, since it is a cosine function, the maximum value is 1. And this will be achieved when theta v is equal to theta I, which in other words means that the load is resistive. In order to minimize the loss in the transmission line, we will introduce a compensating impedance at the customer load to achieve this increased power factor. In other words, we will correct the power factor with the new impedance. The corrected power factor is denoted as PFC and corresponding angle is theta C. The impedance of the load can be represented as Z is equal to R plus JX, and similarly the compensating impedance can be represented as ZC is equal to RC plus JXC. Z is the combined impedance of the load consisting of the resistor and the inductor, and the current I to this impedance will not change because we want to deliver the same amount of net power. However, the IL will change because a new current will pass through the compensating impedance, and we don't want the compensating impedance to absorb average power. Therefore, we will select a reactive element and we will not have a resistive part which would absorb power. And finally, we can write the total parallel load Zp is equal to Zc in parallel with Z, and that will be another Rp plus Jxp. So our job is to find the Xc which will minimize the power absorbed in the transmission line by increasing the corrected power factor. So in this lecture we will not enter to the details of this, but in general you have seen how we do load compensation in a very simple power grid model. For resistive circuits, we learned that the maximum power is transferred from a source to a load when the load resistance is set equal to the Thevenin resistance of the Thevenin equivalent source. In other words, RT is equal to RL. Assume that we have a Thevenin equivalent circuit with a load impedance ZL for an AC circuit. The Thevenin equivalent impedance ZT is equal to RT plus JXT, and similarly load impedance can be written as ZL is equal to RL plus JXL. The average power delivered to the load is equal to P is equal to Im squared over 2 times RL. We want to maximize this average power. The phasor current I for the circuit can be given by I is equal to Vt over Zt plus ZL, and this expression is Vt divided by RT plus JXT plus RL plus JXL. We need to find the values of RL and XL to maximize the power transfer. One thing you need to be careful is that we cannot have negative resistances, but we can have negative and positive imaginary loads. So the average power delivered to the load will be given by this expression here. Now we need to find the condition when this will be maximized. So I want to minimize the expression 1. And here I observe that if I were to minimize the denominator, then I can maximize this expression. And firstly, I can start by eliminating this term here. It has a xt plus xl term, and I can set the XL of the load impedance to equal to minus XT, and that way that term will disappear and I will end up with this term. And obviously this term is identical to the term which I had for the maximum power transfer for resistive circuits. And that can be maximized if I find the first derivative of the power with respect to RL, and the result of that is RT is equal to RL. In other words, the load impedance for maximum power transfer becomes ZL is equal to RT minus JXT. In other words, I will have the same resistive value, but the imaginary value xt due to an inductive or a reactive load will be with the minus sign. In other words, the maximum power transfer occurs when ZL is equal to Z Thevenin conjugate. Alright, let's solidify this concept by solving an example. Find the load impedance that transfers the maximum power to the load and determine the maximum power delivered. So obviously ZL will be equal to Z Thevenin conjugate, which is equal to 5 plus J6 ohms. And accordingly, I should calculate the current I, which is equal to 10 with an angle of 0 volts divided by ZL plus ZT, which is equal to 10 with an angle of 0 divided by 10 ohms, which is equal to 1 with an angle of 0 amperes. Now, after I find this, I can find also the power delivered to the load, which will be equal to Im squared, or I squared here in this case, because I defined it as I, divided by 2 times RL, which is equal to 1 over 2 times 5, which is equal to 2.5 watts. So in other words, I will be maximizing the power delivered to the load with the Z load is equal to 5 plus J6 ohms, and then the maximum power delivered will be 2.5 watts.